In this video, we will see interrelation between the properties of a convex function, and we will see that those are implying the same thing, and one property implies the other property, and we will see visual demonstration of a gradient of a function, how it will look like. So this is basically outline of this video. These two things we will cover, and in first part we will have a deeper dive into the properties of a convex function, and in a second part we will see the visualization of a gradient, that how it will look like. So in last class, if you remember that we have defined a property of a convex function for a very simple function where input is only of a single variable. We are not considering a multivariable function for now. So if there is a single variable function and if it is a convex, then it will satisfy these three properties, and if you prove it is satisfying any one of this property, it will ultimately imply that all other three properties are getting satisfied. So one property implies the second property. There is a bidirectional implication. Similarly, second property implies the third property, and similarly first property implies the third property. So all are getting implied bidirectionally, and let's analyze each of these property one by one. So first property says that for any 2 points on the function x1 and x2, the function value at any point in between those 2 points will be less or equal to the value of a line joining f of x1 and f of x2. So verbally you can say that the line joining any 2 points on a function is always above than the function curve. And if we consider the very simple function, very simple convex function y equal to x square, so the y-axis corresponding to f of x and x-axis corresponding to x. Now you take any 2 points x1 and x2 on this particular x-axis. So let's say I take this particular point as x1 and I take another point as x2. Now you evaluate the function value on those 2 points. So here the function value comes out to be f of x1 here, and here it will comes out to be f of x2 here. If you notice that if you draw a line adjoining both of these points, so in particular this particular green line will be always above than the curve between those 2 points, function curve between those 2 points, that's the gray curve. So green line will be above than the gray curve. Similarly, you can take any 2 points, more specifically instead of x1 and x2 here you can take any 2 points. Let's say you take 1 point here and 1 point here. You draw a line, and whatever the green line you are obtaining, and this green line will be always above than the function curve, which is denoted by the gray curve. More specifically, I am highlighting the curve between the newer points as this particular curve. This curve will be always below than the line joining these 2 points. So that is the first property. Second property says that you evaluate a differentiation at any point x, and you take a deviation epsilon. The function value at f of x plus epsilon will be greater or equal to fx plus epsilon times f prime of x. So verbally you can say that tangent drawn at any point is always below than the function curve. So if we visualize it, let's say this is a x point, this is a x point, and this is a f of x. Now if I draw a tangent will look something like this, right? Now here this is the tangent. You consider any deviation epsilon from this particular tangent. So I have taken this particular deviation x plus epsilon here, and the function value at that particular point, let me denote it with particular green color. So value at green color will be always below than the function value, which I will denote the function value at x plus epsilon by this particular pink color. So pink color will be always above than the green color. You can draw a tangent at any other point. So let's say I draw a tangent here. I consider x as this particular point, let's say here, and I consider a function value f of x at this particular point. Now I again draw a tangent by this particular orange line. Let me draw a tangent, and I consider a deviation epsilon at this particular point. So let me take a deviation epsilon and I consider a new point x plus epsilon as this point. I evaluate a function value at this point by this particular pink color. So the pink color will be somewhere here, and the value on line at x plus epsilon will be here, which I have denoted with this green dot. So green dot will be always lower than the pink dot. So that's what it says, the second property. And the third property says that if we double differentiate the function at any point x, the double differentiation will be greater or equal to 0. Visually, verbally, if you want to say that the slope of tangent is always increasing as x is increasing. So here if you say that let's say x is here, there is some slope of tangent here. So if I start at here and there is some slope here, it is somewhat negative slope, but it will have a certain value. If I slowly increase the x, you will notice that in this particular curve it will have a slope value increasing. It will still be negative, but it will not be that negative. It will be lesser negative, so it is increasing. As I increase x, it will be increasing. At certain point it will become 0. So at x is equal to 0, it is exactly 0. When x is greater than 0, it will be again sort of increasing. So all these three properties are very much interrelated, and you can think of it by interpreting like this, that a convex function will not have any kind of peak kind of shape. So at any point, if you consider a last property, let's say I consider this point, first of all let me draw x-axis and y-axis. So let's say this is x-axis and this is a y-axis, right? Now at any point x, you draw a tangent. Now here I have drawn a tangent. Let's say I have come up with some tangent at this particular direction. Now you slightly evaluate x at somewhat x plus epsilon point, which is slightly more than the x. So here you evaluate a function which will not be exactly on the tangent but somewhere near the tangent. We know this by the Taylor series approximation. So it will be somewhere here, but the tangent will be increasing. So slowly the tangent will be increasing. Slowly again the tangent will be increasing. Slowly tangent will be increasing. So here if you see that the slope of tangent will be non-decreasing or always increasing. It will never decrease. So that's the property of the convex function. And here if you see that the slope of tangent is always steadily increasing. So this will form a certain bowl kind of shape. If you draw a certain curve like this, it will form a certain bowl kind of shape. And this property will imply all these three property, because you evaluate a tangent at any point. So I have evaluated a tangent at multiple points. So let's consider one of the points. So let's consider this particular point. Here I have already evaluated the tangent. Tangent will be always below than the curve. That's what we are saying visually also. This will get definitely implied because of the property that the slope of tangents are steadily increasing for the convex function. The first property also says that if you draw a line adjoining function value at any 2 points, so let's say x1 and x2. So let's say I have considered one function x1 here and another function x2 here. So I have drawn a line adjoining any 2 points x1 and x2. Now this particular pink line will be always above than the function line, which will be gray line in this particular case. So this will visually get satisfied, and all these three properties are very much interrelated. So when I say it will not have a peak kind of shape, so usually we understand a peak kind of shape something like this. It will not have this kind of shape. So if it will have this kind of shape, then you will notice that the tangent at any of the points, so at this particular point, will be above than the function curve. Also if I draw a line adjoining any 2 points, connecting the function value on those 2 points will be below than the function curve. That is the violation of the property for the convex function. So visually you can understand the convex function like that it will not have this peak kind of shape. Also it will not have this kind of shape. So this kind of shape, right? So you can consider any any line which connecting any 2 points, which I have denoted with this particular pink color. So it will not have this kind of shape. The function will not, the function value will not be more than the value on the line on those particular points. So it will not have either this pink kind of shape, or even this kind of shape it will not have. So this is the property of the convex function. So let's analyze the second property bit more. It is saying that the tangent drawn at any point is always below than the function curve, and that's the second property. Now if you form a Taylor series formulation of a function f at x plus epsilon point, then you will get multiple terms. So the first term indicates f of x, plus second term epsilon times f prime x, third term epsilon prime epsilon square by 2 f double prime x. All these terms you will get, and the property which says that f of x plus epsilon will be always greater or equal to f of x plus epsilon times f prime x. So that means the LHS will be always greater or equal to first two terms. So that says that this terms which is of a degree 2 and more than 2, the sum of these terms will be always greater or equal to 0. So this is a property of the convex function, that this is, please note that this particular term that I have indicated using the pink color, it is exactly the RHS of this particular property, and LHS is same as the LHS of this particular property, so LHS of this function. So please note that only if I sum all the term having degree 2 and more, if the sum is greater or equal to 0, then we can say that the function is convex. So we can verbally say that convex function is increasing with the faster rate than the slope of tangent at any point. So that's what we have seen it earlier also. So every time slope of tangent is steadily increasing, and convex function is increasing with a faster and faster rate. So that's the property of the convex function. So let me try to visually show you how it will happen. So first of all, let me consider any point. Let's say I consider this point as x0 first. Now there is a slope of tangent at this particular point, which will be some value. So this tangent, let me denote it with this particular color, which is a orange color. Now I take a small deviation, and I consider a point x1 at this point. I will draw a tangent here again, and here the tangent will be having slightly more slope. Here again I will take another point which is x2, and I will again draw a tangent, and this particular tangent will have a slope which will be slightly this. Now the thing it is saying that the function value at x1 will be greater or equal to f of x0 plus x1 minus x0 times f prime of x0. So that means if I draw a line which is approximating this function value, and what is the actual function value, there will be certain difference, and function value will be always larger. So this particular difference, let me indicate using the green curve. So this is a linear approximation of a function at x1, and whatever the actual function value, the difference between the linear approximation and the actual function value, I have indicated using the green line. Now again let me try to approximate the function value at x2 from the linear approximation of a function at x0. So I will extend this particular line, and at this particular point, this particular linear approximation is something like this, and the actual function value is very large actually. So actual function value, the difference between linear approximation and the actual function value, I have indicated using the pink color. So even though visually you can say that the deviation of x1 from x0 is approximately same than the deviation of x2 than x1. So we are seeing that x2 minus x0 x1 is same as x1 minus x0. The deviation is same, but still if you see that pink line is more than double of the green line. So ideally if you do a twice of the deviation, if it is steadily increasing at somewhat linear rate, then the pink line will be somewhat near to the twice of the green line, since x2 minus x0 will be twice of the x1 minus x0. But the function is not linearly increasing, it is increasing with a rate more than the linear rate. So we can say that the pink line is more than a twice of a green line. So intuitively I have tried to explain that all these three properties are somewhat conveying the same thing, and you can understand the convex function like having the property that it is does not having this particular peak kind of shape anywhere, and steadily it is increasing, gradient is steadily increasing, and that's the property of the convex function. So let us combine all of this and try to see the properties of the convex function in one go. So let me take one point x0 and let me draw a line. So tangent line at x0 will be somewhere here, so I have drawn this tangent x0. Okay, so this is one thing. Now let me draw two things. I take 2 points x1 and x2. So let me take one point x1 here and another point x2 here. So this line joining x1 and x2 is this particular green line, and by the property of a convex function, this green line will be above than the curve between x0 and x1. Similarly, line joining f of x0 and f of x2 is this particular second green line, and for the second green line also this property is getting satisfied. Obviously you can notice the steadiness of the slope change of this particular green line. Slowly this slope of this green line is changing. If I consider x3, which is very close to x0, then x1 and x2, then this green line will slowly come closer to the orange line, and it will be always the case as long as you are considering two different points on this function. You consider x4 again, and again you draw a green line. The slope of the green line will be slowly becoming closer and closer than the tangent slope. So visually you can say that all this green line will have a larger slope than the orange line, and informally you can say that green line is above than the function value or a function curve, and function curve is above than the orange line, which is the tangent, and this is a property of the convex function. Green lines are above than function curve, and function curve is above than tangent line, which is a orange line. Fine. So let's come back to the definition of the gradient. So if there is a function f which is actually having a domain r square and the range r, then the gradient of the function f is defined as a partial derivation of a function f with respect to partial derivation of function f with respect to x, that is the first coordinate, and partial derivation of f with respect to y, that is the second coordinate. And gradient is also a function which is r square to r square. This we have already seen in our previous lectures. So let's visually try to see what does this gradient mean. So I have taken this particular function for two variables. So there are two variables x and y, and this is the function, and this particular function I have demonstrated using this particular curve. So let me denote the axis first. So what is the x-axis in this particular case? It is not explicitly mentioned, but this particular axis is the x-axis here. This axis, x-axis. What is the y-axis in this particular case? The other case is a y-axis, and if whatever the vertical line you are seeing, it is demonstrating the function value. So it will demonstrate the output of f of xy, at every point. So it is a slanted view of this particular two-dimensional input function. Now what will be the gradient at a various points? So let's try to analyze these gradients. So the gradient, if you see that by definition, so gradient of f is just a certain vector del f by del x and del f by del y. That is a gradient. Please know, so this is a 0, okay. Now this is a 2, this is a 4. So there is certain point which is at a 3 3. So at a 3 3 the function value is having a minima, and what will be the gradient of this particular function at 3 3. So I'm asking grade f at this particular value 3 and 3. So if you try to find a partial derivation, you will notice that del f by del x at 3 3 is 0, and del f by del y at 3 3 is also 0. So this gradient is actually 0 vector, and this visually, if you try to see this particular point, it coincides at this particular point. And here if you see that on x-axis the function value, if you draw a tangent, it is having a 0 slope, and similarly for if you draw a tangent along the y-axis, it will also having a 0 slope. So the rate of change of a function at along the x and y direction, both are having a 0 value, so the gradient will also have a value 0. So hopefully that is fine. Now let me ask you one more thing. What will be the gradient of a function at this particular point, which is I am considering a gradient at new point, which is I am keeping the coordinate x as same, which is 3, and I am changing the coordinate of y, and I am considering this new coordinate y, which is 0, let's say. Now if you notice y is 0 at this particular line, which is x-axis, and x is 3 only. So the new point, which will be slightly becoming in this direction, these will be new points that we are interested in. And if you notice at this particular point, the function ball shape is having this kind of behavior. So the function value exactly is somewhere here. And if you notice along the y-axis, the function value is changing, but along the x-axis, the function value is having a 0 slope. So del f by del y will be not equal to 0, but del f by del x will be 0. That means whatever the gradient you will be finding will be on the y-axis direction. So it will be certain vector which will be on a y-axis direction. So hopefully it is the component on x-axis will be 0. So it will having this kind of vector at the point 3 0. Similarly, let me consider a gradient at this particular point, which is grade of f at 0 3. So where does the 0 3 point comes in this particular curve? Now I am keeping the y coordinate as 3 only, but I am keeping the x coordinate 0. So 0 3 point come somewhere here. The x coordinate is 0, that means it is on a y axis, and y coordinate is 3. So this is the point that we are interested in. This point has, this was the 3 3 point, now this point has become this. Now if you try to see the function value at this particular point, you will notice it is having this particular value. Now if you notice at this particular value, the change of a function on a x-axis direction is non-zero, but a change of a function on a y-axis direction is 0. That means this particular tangent at y is having 0 slope, which I have partially indicated using the pink color, it is having a 0 slope, but change of the function on the x-axis is non-zero. That means whatever the gradient you will find, it will be having on the direction x-axis, so it will having this kind of direction. And del f by del x will be non-zero in this particular case, and del f by del y will be 0 in this particular case. Now let's evaluate the gradient at this point, which is 5 5. Both coordinates are 5. Now let's try to evaluate a gradient from the formula. So del f by del x, what it will come? So del f by del x, the equation, if you try to see the partial derivation, it will become 2 times x minus 3, and del f by del y is 2 times y minus 3, and again 2 will be get multiplied because it is already 2 in the function. Now if I evaluate del f by del x and del f by del y at this particular point 5 5, then I will get the formula, which will be del f by del x is 4 and del f by del y is 8. Now if you see that change on y-axis is more than the rate of change on the x-axis. So in this particular diagram, this particular component which I have indicated using this particular orange color, which will having lesser value than the component that I have indicated on the y-axis direction, which I have indicated using the pink color, which will have a lower, which will have a higher value compared to the orange component. So del f by del y is higher than the del f by del x. So whatever the gradient you will see, which I am indicated in using the green color in this particular case, which will having a more component on the y-axis than the x-axis. So it will be somewhat like this. So this is visually we can evaluate the gradient and find out the gradient of the function. There is one more nice interpretation of a gradient, which involves relation with the contours of a function. So first let us define what is a level curve and what is a contour. So level curve is some curve consisting of all points having the same functional value. So here in earlier diagram we have seen this particular function. Now what I am saying is you only consider xy points and you draw a certain curve where all the points on this curve will have the same function value. That's what I mean. So we will see it visually also, and contours is nothing but the collection of the level curves. So let's try to see using this particular example. Now I am considering a function which is I have indicated in this particular slide using a z. You can consider it as a f of function f having a input variable x and y. So z is a f of xy. Now there are two variable function x and y. Now the function is x square plus y square. Now this particular diagram is involving two axes. So let me clarify the axis first. So this is a x-axis which is indicating the value of the input variable x, and similarly this is a y which is involving the value of a input variable y. Now I am considering all the points where a function value is same. So obviously this x square plus y square is a equation of a certain if you equate it to certain constant, so x square plus y square equal to 10, x square plus y square equal to 15, all these are equation of a circle with higher and higher radius. So let's say I equate it with x square plus y square equal to 1. This is certain equation of a function, and this I will get certain points, and this particular equation of a circle I will indicate using this particular orange color. So this orange color indicates all these points having x square plus y square equal to 1. So all these points, all the orange points will have a same function value, which will be 1 in this case. Now I draw another circle which I indicate using the blue color, which is x square plus y square is equal to 2. So this is another. So this orange curve is a level curve. This blue curve is also a level curve. I will draw another curve which is I will indicate using the green color, which is x square plus y square equal to 4. that I have indicated using the green color. This is also another level curve. And now collection of these all the level curves are the contours of the function x square plus y square. So two variable function, I can plot the contours on the Cartesian coordinate x. And similarly, if I consider another function x square minus y square, so I will draw contours something like that. So innermost x square plus y square equal x square minus y square equal to 1. All the points consisting of x square minus y square equal to 1, I will draw it using the orange curve. So this is z equal to 1 points. This is also z equal to 1 points. This is also z equal to 1 points. This is also z equal to 1 points. Similarly, let me draw x square plus x square minus y square equal to 2. All the points consisting x square minus y square equal to 2. So I will draw it using the blue color. So this is another set of points consisting of x square minus y square equal to 2. So all the blue points will have a same function value. All the orange point will have a same function value. Likewise, this is also having a set of points consisting x square minus y square equal to 2. Similarly, let's consider a function value x square minus y square equal to 4. So this is I indicate them using the green color. This is another green color point. This is another green color. This is another green color. Okay. So let's try to see these particular functions 3D way. So this is certain site I am using, which is GeoGebra. It is giving some 3D diagram of an input function. So please note the function I am considering is x square plus y square. Here I am showing the level curve. So these are certain circles you are seeing. They have not shown it using different colors, but it is understandable that all the points on a inner circle will have a same function value. All the points on an outer circle will have a same function value. Now I am considering certain point which is x0 is equal to x0 and y0. First of all, I consider it, let's say 1 point, consider any point, let's say 1.5 and 1.5. Okay. So obviously due to symmetry of the function, whatever the gradient you will have will be 45-degree angle, and del f by del x and del f by del y both will be same. Here if you see it 3D way, the function is looking like this, and it is slowly increasing, and all the the contours are made in such a way that you slice this particular function, and whatever the points you are obtaining, you project them on the xy axis, so that will form a contours on a certain value. So you slice it at function value 2, then you will obtain a contours of function for a function value 2. You slice it at function value 4, then you will obtain a function value which is at 4, and likewise. So if you see that gradient is something like this, which is you will notice that it is actually perpendicular to the contours that you have shown. So this is a property of the gradient. It will always be the perpendicular to the contours that you are showing. So let me change the coefficient of the y square. Now I am changing the coefficient of the y square and making it 3. So please see how the gradient line is changing. So this gradient line is indicated using this particular green color. So if I change it, so obviously these contours will now become ellipse, and rate of change on a y-axis will be sharper than the rate of change on the x-axis. So whatever the gradient is slightly tilted towards the y-axis now. If I slightly more change it, it will even more be tilted. So I will consider x square plus 7y square now. So this gradient direction is even more tilted, and you can visualize this particular ellipse in a 3D in this particular way, and the contours are obtained using this particular manner. You consider a function value constant, you slice that, you consider all this function and function points, and you project it onto the xy plane. So this is a visual demonstration, and you can notice that this gradient will be always perpendicular to the contours that you are drawing. So these new contours, these are two level curves. If I draw more and more level curves at this particular point 1.5 and 1.5, these contours will be exactly perpendicular. And let me change this particular function value, so you will notice that. So if you see that it is becoming perpendicular to the function, right? Even if I change it, right, it is perpendicular to the contours always. Gradient is always perpendicular to the contours. That is the property. It is perpendicular, right? Now it is also perpendicular. Here also it is perpendicular. So that's the property of the gradient. It will be perpendicular to the contours. Also, there is one more way to interpret the gradient. It is a direction of steepest ascent. So these contours, the perpendicular to the contour is direction where the function value is changing most drastically or a highest rate. So the gradient direction is also a direction of a steepest ascent of the function. So here if you see using this particular diagram, in this particular diagram, since at x0 is equal to 1 and y0 minus 0.2, whatever the direction you are showing, it is a perpendicular to it, and it is the steepest ascent direction of a function always. So this is one more property. So it will become more clear if you see x0 and y0 same value, and since I change the coefficient of y, it is slightly becoming more and more tilted towards the y-axis. So since small change in y-axis is making a rapid change on the function value, so the gradient is also being tilted towards the y-axis. So this is one more way of interpreting it, that gradient direction is a steepest ascent direction of a function. So it is a direction where the function value is changing most drastically. It is same way of saying that the perpendicular of the contour direction is also a gradient direction. Both are same thing. So this is I have already mentioned, gradient at any point is a direction of steepest increase of a function. Now and it will be also perpendicular to the contour at that point. So thank you very much for watching this video, and we will meet you in the next video.